So, hello again. Welcome to the last part of Stark one-on-one. In this part, we are going to speak about the proof and the way that the prover is going to convince the verifier that he actually computed correctly all the computation. In approximately 1 hour, you are going to become a Stark expert after this talk and after the coding. So, before we will start, let's have another short recap. So in the first talk, we computed the trace, and actually when I say trace, I mean the trace on the low degree extension, on the LDE, and we committed on the trace by sending the trace route to the verifier. In the second talk, we computed the composition polynomial, and again, the composition polynomial on a low degree extension, and we committed on the composition polynomial by sending the CP route. Then in the last talk, we've computed each file layer, CP1, CP2 until CP10. And for each layer, we committed on that layer by sending CP at level I, the CP route at level I. So until now, what we actually did is to send all those commitments from the prover to the verifier. We send the trace route, the CP route, and CP1 until CP10 routes. This is what we've sent to the verifier from the prover. So the entire proof contains two parts. The first one is the commitment, what we've just covered in the first 3 talks. In this talk, we are going to speak about the way that the prover will convince the verifier that the computation that he did was done correctly. So how can the prover convince the verifier? Again, my first intuition was that the prover going to convince the verifier by just begging to him and begging him and to tell him, please believe me. And again, we are mathematicians, and they told me that we cannot do it and we need to use more mathematical way. So we will do it in a different way, unfortunately. And it will be by the verifier will send Q random elements. And for each element, the prover going to send validation data for the verifier. So what is the validation data? What is the validation data that the prover needs to send to the verifier? The validation data is the data that will allow the prover convince the verifier that each transition was done correctly. Each computation that the prover computed before was done correctly. So the first thing that the prover needs to convince the verifier is that the transition between the trace to the composition polynomial was done correctly. This is the computation that you saw in the second talk. And how can he do it? So the prover will send to the verifier for some x, he will send him f of x, f of gx, and f of g square x. The verifier will be able to compute by himself CP0 of x. How will he do it? If we will remember in the second talk, we've seen how the prover computes CP0 of x by using those 3 values. So the verifier will be able to compute it by himself. And he will be able to compute CP0 of x, and then he will be convinced that the prover computed that correctly. The second thing that we want to convince the verifier is that the transition between 2 consecutive file layers. So, as you probably remember, CPI of x is gx squared plus x of hx squared. So, therefore, CPI of minus x is gx squared minus x hx squared. So if we play a little bit with the elements, we can express g of x squared and h of x squared with only CPx and CP minus x. Let us remember that CPI plus 1 of x squared is g of x squared plus beta h of x squared. It's exactly what we've seen in the last talk. So the bottom line from all those equations, and this is the main important thing here, is that we can compute CP at layer I plus 1 of x squared by only using CP at layer I of x and minus x. I'm repeating it because it's important. We can compute CP of x squared at layer I plus 1 with only CP of x and minus x at layer I. So how we are going to use it? The prover will send to the verifier CP of x and CP of minus x at layer 0. The verifier will be able to compute by himself CP at layer 1 of x squared. He will compute it by himself, and then he will verify that the computation that the prover did was done correctly, and he computed that correctly. Then the prover will send to the verifier CP at layer 1 of minus x squared, and he will be able to compute CP at layer 2 of x to the power of 4, and repeatedly again and again. So now we will speak about the decommitment phase. The verifier will send to the prover a query at point x, and we will see now what the prover is going to send to the verifier. So at first, the prover needs to send to the verifier, as we've just seen, f of x, f of gx, and f of g square x. And when I'm saying f of x, f of gx, and f of g square x, I'm actually talking about only the element. But how the prover can know, how the prover can convince the verifier that we actually commit on each one of those elements. As you probably remember, we didn't send all of this element. We've just sent the root of the hash of the Merkle tree. So we have here the Merkle tree, and we've just sent the hash. So for each element, we need to send the authentication path from the prover to the verifier, and in that way, the prover convinced the verifier that he actually committed on this element, that the root that he sent in the previous steps was actually contain all of these elements. So at first, the prover sent to the verifier f of x, f of gx, and f of g squared of x, and for each one of them, the authentication path. The authentication path is at length of order of log n information, because it's the length of the path from the leaf to the root. Then the verifier will compute CP at layer 0 of x, and will actually check that what the prover sent him before is actually the same value with the authentication path. Then the prover will send him CP at layer 0 of x and CP at layer 0 of minus x. The verifier will compute CP at layer 1 of x squared, and he will verify with the authentication path that it's exactly the same value that the prover committed before. And this can be done again and again with CP at layer 1 of minus x squared, and the verifier will compute by himself CP at layer 2 of x to the power of 4, and will verify that it did actually, the prover sent him this exact value before, and he will do it repeated again and again until CP at layer 10 of x to the power of 1k. So this concludes the entire proof. So in the first 3 talks, you saw the commitment that the prover commit and send to the verifier. And now we've just seen what the prover sends to the verifier for each query in order to convince the verifier that he actually did all the computation correctly. So now we still need to understand how much data does the prover send to the verifier to convince him. So this is the data that for each step the prover sent to the verifier. For the first layer, for the trace root, you need to send 3 elements, and for each element the authentication path. And then for each fry layer, we need to send 2 elements and the authentication path. The first 3 elements is in order to convince the verifier that the transition between the trace to the composition polynomial was done correctly. And then each 2 consecutive elements is in order to allow the prover convince the verifier that the transition between each 2 Fry layers was done correctly. So if our trace length is n, in this case 1023, there are order of log n information that the prover needs to send. Order of log n elements. For each element, the prover needs to send the element and the authentication path. The authentication path is at length of order of log n. So in total, the prover needs to send to the verifier order of log square n information for each single query. Order of log n elements, and for each element, the authentication path with order of log n. So in total, order of log square n information. And this was for one single query. And for q different queries, we need to send q multiply by order of log square information. Because for each different query, we need to send all the data that we've just seen. We need to send f of x, f of gx, f of g square of x for the first layer, and then we need to send cp at layer I of x and minus x, and of course with the authentication path. Q is constant because it's the number of queries that we need, and order of log square n information. So this concludes the entire proof and the data that the prover sent to the verifier in order to convince him. After he sends all the data, the prover can convince the verifier, and the verifier is convinced that we did the computation correctly, and our goal, and our main goal, the statement on the Fibonacci square sequence was actually correct and was computed as we've just stated. So this concludes the entire Stark proof, and the verifier be convinced after that. So now you're going to code it. You're going to code the decommitment phase. And after you're going to code it, you're going to be a Stark expert, exactly like Eli.